So everything's working? Just the power. Okay, and you got the streaming is good. Okay. In the future, you can wait to start the stream until right at 3. Otherwise, there's not like start playing stuff.
That's like ideally so that'll be like an expansion of the smaller problem and possibly a very hard problem of just like taking a face. Yeah, so we could just do that. So that's just an idea of like if we want to expand it. Yeah, the thing is, there's already stuff out there. Like, there's just text blocks.
Hey everyone, let's get started. So hopefully everyone was able to turn in the homework and then make it a class on time, or at least everyone here. I assume other people are just turned it in and are rushing on their way here. So right now, so were there any problems with submitting the homework on Canvas? Everything went smoothly? Okay, good. So just another reminder, the project proposal is already due next week, Monday. So there's a couple notes either I forgot to say on Wednesday or I didn't emphasize, so let me kind of repeat these about the project. So you need to have a partner or 2 partners on the project, and unless I've explicitly said otherwise, for certain for some special circumstances. So if you can turn in a project proposal without a partner on it, but then you'll lose points. Okay, so this is one of those things where you'll get all the points if you follow the instructions. And then, so we'll try, and it doesn't need to be too detailed. You don't need to be too long at this point. We just want you to kind of start concentrating on a topic, and as we go through the class, you'll get ideas of how to use techniques from class. But I want you to start thinking about the topic now, and start forming your teams and thinking about what you're going to do. Start thinking about how are you going to collect your data. And so the data collection report will be due in roughly a month or so. And so that's the next milestone. You don't have to be using techniques, but you'll need to do some work for that as well. So one question would be about on Canvas, how do you turn in things for the if you have partners? Do you all need to turn stuff in? So I think probably the best idea is for the first time, everyone should plan to turn in, and hopefully it's the exact same copy of the proposal. If only one person from the group turns it in, we'll probably be okay, we'll sort it out. We'll try and create these group structures within Canvas afterwards, after you form groups, so that there's only one submission you have to do after that. I think I can get that to work. Okay, one other thing I mentioned to a number of you, but I think I didn't say on Wednesday, is about doing a project based on classification. So just a fairly arbitrary split, we've decided to, this class does not talk about the main classification task that the machine learning class is often focusing on. So I don't want the main central thing about the project to be about classification. So you can use classification. So you can build better features and then apply a generic classifier at the end, maybe to evaluate it. But the focus of it should be on various techniques or ideas from class, and then you can do whatever you want else on top of that. Okay. But one of the requirements will be what to use from class, and that was classification. That wasn't in class, so that doesn't count. Yeah.
So 2 questions. One is, when is the next assignment going to be posted, do you think?
I'll try and post it this week, if not, hopefully by Monday.
Cool. And the other question is like, what would be a good way for us to like know kind of like the bag of techniques that, because I mean we're only at the start of the semester, right?
Right.
So if I want to like, if I have projects in mind and I want to know like what we're going to cover in this class to make sure that I can use techniques from this class,
Right.
in the project, like.
So if you go to the webpage, I kind of have stuff laid out there. The first lecture, I tried to give an overview of everything in class as kind of a rough idea of what kind of techniques would be there. So hopefully that's enough to kind of get started. You don't need to know the specific technique yet. Hopefully something caught your eye or you have something in mind. If you turn in a proposal and it does not align well with class for some reason, I'm not going to take points off. I'm just going to give you feedback and say, actually, this may or may not work, or maybe I suggest doing something slightly else. So most cases, the proposals are generally fine, but on a few, I'll try and redirect you a little bit. So if you're not sure, you can come talk to me beforehand as well, at some point before you turn it in, or after you turn it in too. You know, you keep the dialogue open. All right, any questions about the proposal? Okay, cool. All right, so then the lecture today is going to be about locality sensitive hashing, and so this will tie together with this will tie together with the n-grams or the k-grams and the min hashing we talked about before. Basically, before we were looking at where you have these documents, you turn them into sets, and then you turn them into these vectors, where the similarity between two vectors v1 and v2 was the expected way we measured the similarity was equal to the Jacquard similarity between the corresponding sets. Okay? And remember, this is not necessarily some notion of similarity to find the documents, but we've already approximated in the first step up here. Okay. So now we have the problem that we have lots. We're going to say we're going to pre-process this for many documents. So let's say we have many documents. So let's say that the number is equal to n. Let's say this is like 1 million. Okay, so there's something like 1 billion web pages out there that Google's crawling, or so 1 billion people on Facebook each have a timeline, right? So there's these, think of these big text documents that are out there that could be larger than 1 million. So let's say 1 million. And so now there'll be two sort of questions that we'll want to try and address. So what items are similar? And remember, this is from this set of items, you want to find all the ones that are more similar than some threshold. So naively, this involves an n-squared algorithm. So you can check all n squared, and each of them you can compute some distance or some similarity using these vectors or going back to the sets. The other question is, so given a query which in the set are similar to the query. And naively, this will take O of n time, because you need to check against each one in the set. Okay? So let's, and this is tricky because these are complex objects, or we have these vectors which will turn out to be nicer to work with. But let's start with thinking about just a problem in one dimension. And let's say I've got some, you know, some data points. Okay, and now the first thing I do is I'm going to say I have some similarity threshold. This is the value S. And I want to find all pairs which are more similar than S, means they're closer together than this threshold. Okay, and so the first thing you might think to do is you can take all the items and you sort them, and you can build like a list between them. And so then the ones, if something is similar, it must be, you know, next to each other in the sorted order, or next to something that's next to you. You can kind of think of sliding, have a window and slide along here, and anything in the same window at the same time or so. And you can get something to work out that works in linear time and answers this first question in linear time. Or, I mean linear time plus the number of things, pairs that are similar. The other question is, given a query, determine are there other points that are within this distance of similarity. So essentially you want to answer which points are in this region here. Right? So this distance here is S. Okay? And so you want to answer this on the query. So if you were to figure out where this was in sorted order, you could scan across until it's there and then just walk back and forth in a list. Again, you could do that, but that takes linear time to scan. So probably if you, from basic data structures, how would you do this more efficiently? What data structure would you build to answer a query to find things that are similar in distances? Okay, so let's say I wanted to answer this question Q2. I have 1 million data points in one dimension. So think of 1 million words or something I can sort. Something I can compare these objects. Let's not worry that they're data points right now. And I have a query, and I want to find all things which are similar. Yeah.
Tree work?
Yeah, right. So you can build a binary tree, right? On a balanced binary tree, and then the query, you know, I won't draw this in full detail here, right? But you build a balanced binary tree. Right, so it looks something like this. So now on a query, you kind of keep a value here that's a pivot at this point in the tree. If the query is smaller than it, you go down to this side, and you kind of walk and find the nearest neighbor. And then if you have these stored in a list, you can walk either direction of the list to find everything that's similar. So you can solve this pretty quickly. It takes takes roughly log n time to walk down the tree, right? Log base 2, the height of the tree. So it's log base 2 plus k, which is the number of similar items. Okay, so this is not the technique we're going to use. So let's say that we can't even sort the items. So we can't use the first technique for Q1 because we can't put them in sorted order, and we don't want to spend this log n factor. but we can use some randomness and we can have some probability of failure. Sometimes we won't find similar names. Okay, so let's relax this a little bit. So let's get rid of this blue part here. Right, so we're going to kind of come back to some ideas based on this. In 2 lectures, next week, Wednesday, that applies to higher dimensional data. But this one, those will have some limitations on the dimension, and they won't work with sets, or the sort of data we have. So let's say we can't sort them, because all I know is that 2 things are similar if their coordinates of the vectors are the same sometimes. So I can't quite sort them, the items, and I can't do the binary search. I don't want to spend this log n. But I'm willing to be much more approximate. I don't care how similar if I get the similarity quite right.
Do some sort of clustering, and then use centroids.
Yeah, so you can think of clustering the data. Yeah.
Especially if you had higher dimension data.
Yeah. So in order to do that, you need to know more information. It's going to turn out to do the clustering. You're first going to have to figure out which things are similar, and we want to answer that question first. But that's a good start. We want to somehow use hash functions some way.
Oh, I was going to say, could you just hash to an index in some sort of linked list, and then wherever you hash to, you just walk a certain distance around that point to find the similar items?
Yeah, so good, right. So this is kind of roughly going to be the right idea. So I'm going to kind of present a different idea, and then we're going to start over fresh and build up this locality sense of hashing in higher dimensions. So let me explain. Kind of instead of doing kind of a hashing by itself, what we're going to do is we're going to put down a grid on the data. So I'm going to put these boundaries between grid cells. And so now all I'm going to do is I'm going to map each data point to one of these buckets. Right? We'll call this B1, B2, B3, B4, B5, B6. Okay, so now I'm just going to say, if this data point falls here, it's in bucket B4. And so now, kind of the idea is that if 2 data points are similar, they're going to tend to fall in the same bucket. So this query point fell in the same bucket as this point, and those points are similar. Okay, so now I have some choice of how I shifted this bucket, so I might do this a few times with different randomly shifted back and forth a little bit. Because this data point here is similar here, but if I drew the buckets in a way that was different, I have color here, if I drew the boundary here instead, and so forth. If I drew the boundary here, then according to these purple buckets, these 2 points are not similar anymore. Okay, so I may have to do this a few times to check to see if they keep falling in the same bucket or not. Okay. Now, it turns out because, now with the Jacquard similarity, I kind of have something like these buckets already. I don't actually need to use the one-dimensional ordering. I just say if the coordinates are the same, if the first coordinate of the vectors are the same, they're in the same bucket. That's essentially what that coordinate is going to mean. So I'm going to use this idea. Okay, so and kind of the more times they fall in the same bucket, like sometimes these do, sometimes they don't, sometimes these do, sometimes they don't. The more times they fall in the same bucket, the more similar they're going to be. And this is kind of like with the Jacquard similarity. The more intersections that the vectors have, the higher there's going to be, the higher the Jacquard similarity, because the expected similarity, which is the expected number of collisions there, is exactly equal to the Jacquard similarity. So we want to kind of use this property. Okay, so this is kind of the idea we're going to try and exploit. So let me kind of write something general first about the properties that you need, give you a general overview of what you need for locality-sensitive hashing, and then I'll get a little bit more, walk through the example with the vectors we have for the Jacquard similarity. So the properties we need are, we want to talk about a hash function, or this is a hash function from a family of hash functions. We're going to say that this is kind of a mouthful, but gamma, phi, alpha, beta. So similar, if it has the following two properties, the probability that the hash of any two objects A and B is going to be greater than alpha if the distance between A and B are going to be less than gamma, and the probability that h of A equals h of B should be less than beta if the distance A, B is greater than phi. Okay, so basically the way to think of this is that there's going to be some distance. We'll call this distance tau. And so now there'll be two other distances of interest, gamma and phi. Okay, so now we want to say if the distance between them, if the distance is less than gamma, then I want the probability to be high. So now I want the probability of collision to be greater than alpha, to be greater than some value. And if it's out here, if it's out in this range, I want the probability to be less than beta. Okay, so I want it to be smaller than, so I want the probability of collision to be small if they're far apart and large if they're close. And so there's some tau threshold I'm interested in, and I kind of give myself some slack. Okay, so this is technically the definition. In the case of locality-sensitive hashing, what we're going to actually do is this, we're going to have gamma equals tau equals phi. So they're going to be the same. I'm going to kind of push these together. But you can do it, it doesn't need to be that strict. You can allow us a little bit of gap here and things will still work. And then the probability is going to be exactly equal to this similarity, which will be between 0 and 1 somewhere. It doesn't matter what the threshold is, which just, it more depends on these alpha and beta with respect to how big this gap is. Okay. So this is the technical properties, and so we'll talk about this for the Jacquard similarity case, and then I'll talk about another case as well that will also follow these. And hopefully you'll see the pattern. Okay, so we'll come back to that and see what that definition means. Okay, so now to review, so we had these meta-hashes, HI, which went from this set of n objects to another set of n, or maybe this was log n objects, to kind of say that probably you didn't have any collisions, or you didn't have too many collisions. And so now you can think of these hash functions. So if you had objects set 1, set 2, up through set n, they each correspond to a vector. So you have the value v1, v2, up to vk. That's for, so this is the vector then of this set. And you got this from this hash function 1, hash function 2, up to hash function k. And so now, remember this was our data. And we have the property that the Jacquard similarity between S1 and S2 is equal to the expected number of rows. If hi of S1 equals hi of S, this is the sum, okay, S2. Okay, so, all right, so this is what we want to use, and so now what we have is this property. We have, instead of these shifting bins we had in one dimension, we have these hash functions that collide if we, they're more likely to collide if things are more similar, which is what we want. But how do we answer these two questions? Let's say, how do I use all these hash functions to quickly find, say, so this, given a query, all the other points which are similar, right? So I now have a query, say Q, and I'm going to get a vector, you know, for this query as well. Right, so I'm going to get a query document. I want to find similar documents in the set. Okay, how do I use these hash functions to quickly find this? So there are kind of two obvious ways you can kind of think about doing this and say, if I just look at one hash function, that's not a very good estimate. I could be off, right? If the similarity is 0.1, then if there are 10 hash functions that have similarity 0.1, probably one of them collides. If I look at just that one hash, you know, if I have 10 sets that have similarity 0.1, probably one of them is going to collide with any hash function I look at. It doesn't mean that one is much more similar than the others. Okay, so one way of saying I want to try and amplify this probability by using these repeated measurements. So I want to say they're similar if all hash functions collide. So if all the hash functions collide, so I say, well, if it, you know, I don't just want to say one hash function collides, that, you know, that's not enough. I need to repeat this a bunch of times, right? So if I go up here, I said, well, you know, I don't just want to say one because it's not that similar. I want to try a bunch of these hash functions and make sure it keeps colliding over and over again. Okay, so I'm going to get fewer. I'm going to get rid of these false positives that look like they were similar but really weren't similar. Okay, but the problem with this is that things that are similar eventually, just by chance, one of the hash functions won't collide. So you'll start throwing out good things. So this is too harsh. So this one is too harsh. So the other way of saying is, well, if I'm too harsh there and I'm missing all these good other data points which are similar, but you know I'm not finding them because the hash function just didn't happen to collide, then I'm saying they're similar if any of the hash functions collide. Okay, so I try one hash function, it didn't collide, but I'll try another one because, you know, I may have missed it the first time, and then maybe I can try and filter them afterwards. But you know, this one is too nice. You're going to have a lot of these false positives, things that you think are similar but aren't. Okay, so I like to kind of think of this one as the papa bear, and this one as the mama bear. right? So the papa bear is too harsh, the mama bear is too nice, or the papa bear's porridge is too hot, the mama bear's porridge is too cold. We want something in the middle here. We want to combine these together. How would you combine these ideas together? How would you get the baby bear? The baby bear's way of doing this is going to be just right, somewhere in the middle. How would you do this?
You have the threshold of collision.
So some fraction of collision. So if over half of them collide. Now, that's good, right? Because I know if I expect the similarity is 0.5, I expect half of them to collide, right? So this is, but the problem is I don't know how to check this quickly, right? Either of these I can check. I can run the hash functions, and if they all collide, I only keep the things that collide the first time, and then I try another one, and if they don't collide, I throw them out. In this second one, if any collide, anytime I see a collision, I add it to my set of similar things. I can do both of these very efficiently. But if I want half of them to collide, that's much harder to keep track of. Can I throw something away if the first two hash functions don't collide? Do I still need to keep track of it, that those things might be similar because the first two didn't collide? I don't know. It becomes trickier. But that's kind of in the right direction. But that's not. I kind of want to use both of these ideas and combine them together. Yeah?
I think we can just keep trying and until we have the first collision, and then we can write down the number, how many times have we tried.
Okay, that's an interesting idea. So try until first collision. So run the mama bear for a while, build up a bunch of potential ones, and of the potential ones, then count. And then so that wasn't what I had. It's a good idea. It wasn't what I had in mind. I don't know if it works. It might actually work. I've seen something like this trick used before for other things to get to work. So this is in the right direction. But this, at least the analysis will not be as straightforward. This one is not exactly what the baby bear is going to do.
Wait, why can't you just have a threshold?
Because I can't keep track of which ones. I'd have to keep track of, for every pair or for every other item, how many. I have to keep a counter of how many of the hash functions are colliding.
Nice.
Right, so it's not efficient.
Yeah.
If I did have those numbers, that's the right way to do it. But I don't want to compute all those. That's going to take. Remember, this is kind of the query problem. I don't want to spend linear time. I just want to spend the time on the ones which are similar. Okay, so what this is going to do is going to use a technique called banding. And the idea is I'm going to have these hash functions. Okay, and so let's say this is one of the ones in the data set, and this is the query one. And so the banding idea is going to be to break this up into these bands. Okay, and so inside of each band, I'm going to run the papa bear. Okay, so I'm going to say that I only care if within each band I have collisions in all locations. So this is this one is good, this one is good, this one is not good. So this one fails papa. He's like, that's it. One mistake, you're out. Right? Very harsh. I shouldn't be using stereotypes, but this is the ones from the book. Not all papas are like this. Okay, and then this one, had some problems at the beginning. He never even paid attention to them, right? You know, and then finally in this one it was good, and then this one had some problems. Okay, so one thing had a Papa Bear thing that went great, and then the Mama Bear is sitting down here, and so this one Papa gave a frown, but he's happy here, and Mama said, okay, that's one good thing you did today. You get a cookie, right? So it said, you know, this one is okay. So this one, so Papa Bear is like an and Mama Bear is like an or. So I need to hit any one of these bands. I need to hit everything correctly, and I only need to hit in one of the bands. Okay, and so this kind of is combining both. So basically, the idea is you've got a total of k of these hash functions. And let's see if I get the notation that matches my note. So then I'm going to say B is the number inside of this band. Okay, and so then the Mama Bear is over k divided by b, kind of essential, these more complex hash functions, right? So I've taken a simple hash function and I've combined it together with b other hash functions, and I've essentially gotten a more restrictive hash function here. So I made this harsher, but then I loosened it up with the Mama, okay? And so what happens, I run k over b independent things where I only keep things if they exist. So I run this one in parallel with these other ones, or I do just one at a time. I run this one, then I run this one. And each time I'm doing an and, so if things fall in the same bin, I keep track of them. As soon as anything falls apart, then I can ignore it. One way of thinking about it, again, is to think of this. So these are our hash functions, and this is just the case for b equals 2. And then think of it in 2 dimensions. And if my data points are here, they each fall in, you know, there are 2 hash functions, so they have to fall in this one here and this one here, and then the query, it falls in a grid here. And so if it falls in the same grid cell as this one, I keep it. So I take the result of b hash functions and I use those to kind of hash into a hash table or something like that. And so if there are other things that follow the same hash table, I say those are similar. And I can do k over b trials of this. So I have k over b different hash functions that I'm using, but these are more complex hash functions. So this is now something I can do efficiently, and it's not necessarily too harsh or too easy. We'll analyze next how harsh or easy it is, and how to choose the value b. Question?
Oh yeah, so is it essentially you have like k over b chances to get all your hashes right, but as long as you get 1, then you're similar?
That's right, yeah. Yeah, so in this case, I think I got about slightly more than half of the hashes were correct. I got the 0. The 0 was there correct. But 4 of them were in a row, and that happened once in this band, so I said, okay, these are similar. These are above whatever threshold. And if you want them to be more, if you want the threshold higher or lower, you adjust the value b. Okay, so let's walk through the probability a little bit, how to think about this. Okay, so let's start with, so I'm going to say that this is for the case where the similarity between the two things I'm going to say is a value s. So this is some similarity, and s is going to be in 0 or 1. And I know this is equal to the probability of collision. Okay? Okay, so then, so S is going to be the, is going to be the probability of collision. So then the probability I collide within one of the bands with Papa Bear, these are going to be independent of each other, is going to be S to the power B. Okay, so the probability of collision inside the band. Right, so if S is less than 1, when I do a power, this goes down and goes down quickly, right? So the probability becomes much smaller. Okay, now to analyze it, I want to look at 1 minus S to the B. So this is the probability of no collision in a and this is in one band. In one band. Okay, so now if I have R of these bands, or if I say R is going to be K divided by B, then 1 minus S to the B to the power R is going to be the probability of no collision in R bands. Make sense? Right, and so then the probability of a collision in any band is going to be 1 minus S to the B to the R. The probability of collision in any of our bands. Right? So this is going to be my function that describes the probability that I'm going to return two things as being similar. Right? So if I have a band of size B and I'm going to have R different bands, and the hash function has the property that the probability of collision is S, then this is the probability I'm going to find things which are similar. Okay, so what does this mean? Basically, you're going to get something which is often called an S-curve. You're going to look at S going from 0 to 1, and so you're going to plot F of S. And you'll get something that looks kind of like this. Okay, so hopefully what you want is that some threshold that you want to say it's similar if the similarity is greater than this. And this is the, and then, so this is going to be, this is going to be the probability you say that these are similar. Right, so I take whatever similarity I have. So I want to set some similarity threshold. I want to say they're similar if it's more similar than this. I want to find it similar. So I want the probability to be higher. Remember, this also goes from 0 to 1. Okay, let's be helpful to look at this in a. Okay, so I've actually. All right, so I've plotted this. So I've plotted this where B is equal to 3 and R is equal to 5. And does that do any better? Okay, so B is equal to 3 and R is equal to 5. And so if the threshold was 0.5, then I have about a 50% chance of finding it. If the threshold was 0.75, then I have about 90% chance of finding it, right? So if it's 0.5, it goes to about 90%. Or 0.75, about 90%, right? So and so if it's very unsimilar, I'm unlikely to find it. Okay, so this is with 3 and 5. What's going to happen now if I increase the number of bands that I use? What's the curve going to do? Okay, a new equation. 1 minus sinus. Let's say make this 10. What is this going to look like? So the R was the number of times that, the number of times you're doing the mama bear thing, so you're making it easier. So you're going to find things more likely. You're more likely to say things are similar. So that means that the probability of finding things should go up. So either the curve shifts up, or you can think of it as moving to the left. A smaller similarity is going to find a collision. So that's what happened. It shifted, it moved up. I have a higher probability of finding it. Right? And so now what happens if so now I'm also going to change the effect of the papa bear. I'm going to have more things within a band. I'm going to be harsher. So now the probability should move down, right? Let's make this 10 also. Oh boy. All right, move down here. What also happened? Right, so I started here, I made it easier, and then I made it harder. I bet if I adjusted this one a little bit, it can kind of look similar here. Right, yeah, look at that. So it's going about the same spot as the original curve, but I added more bands, and I made the band, each of the bands larger. What's the important difference between both of these?
Slope.
Yeah, it's slope. It's much steeper. That means I have a lot less things here where I wanted this threshold, but if it's, if it was 0.4, I sometimes said it was okay. Now 25% of the time I said it was okay when it was 0.4 with the new band. The other one, it was like 30% of the time. I'm less likely to make mistakes. The steeper it is, the less likely you're going to make mistakes for some threshold you want. Okay, so the more of these hash functions you have, the more accurate you can get. So I can make this even steeper, right? So let's try and do another one here. Say 6 and say 20. So this one's similar too, but it's even much steeper, so I'm doing even much better. So 0.4 is now only about 15% of the time. Okay, but now the number of bands I need is the product of those two numbers though. Right, so the number of bands is going up kind of quickly, but I'm able to do this better. Okay, so the goal is you want to have kind of as steep a curve as possible, but the steepness is pretty much dependent on the number of hash functions you're willing to have, which is, the more of those, the longer it takes, the more space it takes. And you also want to say some notion of what you think is similar. So these are all good for the similarity is 0.5, but let's say I want something with the similarity of 0.15. I'm going to need to adjust these bands a little bit. Let's see. So let's say I have 6 times 43. About how many is that? That's about, what's that? About 250 per round. So let's say I have about 250 bands. Let's try and choose something that that gives a good threshold around point. Oh, went the wrong way. Both of those are not. Okay, so let's try and make the similarity. Let's do So it's, around the boundaries, it's a little harder to check. Right, so this may be, all right, so I can adjust this band by playing with this ratio. Okay, so you can plot these on your own, and I kind of play with this a little bit. So in the next homework assignment, you're going to have to go from k-grams and then play around with these hash functions. Then do min hashing and play around with this. So, okay, so let's go back to here. Okay, so there's there's like so often the best way to choose the distribution of R and B. So often you have some budget of k, so hash functions, and you need to go to have number hash in a band B, and so the number of bands is going to be R, such that R times B is going to be equal or less than or equal to K. So how do you choose this? Well, you kind of want to choose, and you have some similarity a similarity threshold, tau, and so you kind of want to hit tau. At tau, the things to the more similar are going to have a high probability of being hit, and things less than tau, low probability. So you kind of want to choose it so the slope is largest around tau. And to do that, a kind of rough estimate of this is log base tau of k, and then let's see, then r is going to be equal to k divided by d. Right, so this is kind of a rule of thumb. So I would start, if you're doing this, start with this rule of thumb, and then maybe you can plot it and play around with it. It always helps to plot and see kind of what you're working with. All right. Okay, so do you think you'd see how this would work with, you go from documents and then you have this technique where you can quickly find things that are similar. Also if you were, I talked about the problem where you had a query, you want to find things that are similar to the query. And so it's going to have some error now. Sometimes you're going to return things which are not as similar as you want. And sometimes you're going to miss some things which are similar, right? There's some probability you return the wrong things, or you miss the things that you want. Maybe you want to be more conservative, so you can set the threshold differently based on the S function. You'd rather have false positives than false negatives. There are some technical ways of getting rid of either the false positives or false negatives, but I won't go into those. They're kind of more theoretical tools. But if you remember, when we started from the documents, we modeled them as these sets, then as vectors, and there's some approximation along the way. So if we found something right below the threshold and said, well, we returned it, even though the similarity is a little bit less than we wanted, well, that similarity was some function that we chose. And so it's probably okay if we miss things around the boundary a little bit. If I miss something that was a little bit larger, that's probably not a big deal either, right? So there's some error here, but this whole notion of distance was not some magical ground truth anyway. So it should be acceptable to have some errors in this situation. Now, sometimes if you're working as a data scientist or in a company and you tell that to your boss, that can be tricky. But if you're trying to analyze stuff quickly yourself, you should be able to justify that. Okay, we'll talk about other things that can have some stronger guarantees, but work in more restricted settings next week, Wednesday. Okay. All right, so this was for the min hashing, which had this property that the probability of a collision was exactly the similarity. But I said there's this general framework, and anything that has some variables like this, if you apply it with the banding, it's going to give you something that looks like the this S curve. And it's going to have some gaps in some places, but it will essentially still work, and you can prove things about it, and it works reasonably well in practice as well. I'm going to give you one very kind of common example now, and that's for where instead of caring about the Jacquard similarity or the Jacquard distance, we're going to look at the Euclidean distance between two vectors. We'll call them P and Q, and this is often written as P minus Q. And so this is going to, and if these are going to be points in d-dimensional Euclidean space, you often write it like this. This is a blackboard bold R, and this is d dimensions, right? And so that means that I'm going to calculate the distance as okay, like this. Remember, so this is the Euclidean distance, and we're going to be talking about the case where d is going to be very large, and we somehow want to reduce this to a problem where it's smaller, in fact, to a one-dimensional problem, and then we can use this banding technique. So historically, min-hashing was kind of first invented in this regime, and then they kind of showed that you could do this for Euclidean distance, and then they generalized this approach. So in order to do this, we now need to create some sort of hash function that satisfies those properties, probabilistic properties that I wrote up in magenta for points in high-dimensional space. How would you create a hash function in high-dimensional space that you can calculate easily? So I'm going to show you roughly how this should work in 2 dimensions, and this will generalize as naturally. Okay, so the idea in 2 dimensions is we're going to pick a random unit vector u, and we're going to project all of the points onto this. So they're onto this random unit vector, and then we're going to chop this random unit vector up into bins. So these were the locations. And so if the 2 things fall in the same bin, they're going to be similar by that hash function. Okay, so how would you compute this projection? How would you write this? In your linear algebra class, how do you write a projection onto a unit vector for a data point P u? So the projection onto unit vector u by P, that would be this point here. That's just going to be the dot product, right? The dot product projects it onto there. It actually, it doesn't really give a location on here. I need to multiply by the vector u, but all I need is the distance from the origin, or the directed distance, right? The dot product, remember, is times pi times ui. So I just multiply together the coordinates and add these up. That's the dot product. That projects it. That gives me this value here is the length from the origin onto that point. Okay, and so then my hash function by u is, and I'm going to will be the gamma parameter in those properties that I wrote up. So the mod basically it's going to wrap it around, and then I'm going to take this as an integer. So this is for some large enough value t, for large t, right? So I'm going to so some large t. So I'm going to take mod some very big and then snap it to an integer, right? So round it to an integer. So map it to some large value and then snap it to an integer. Okay. So this is how I create the hash function. There's one more, and I'll come back and analyze how well this works in a minute. But I haven't completely described to you how do you create this hash function? How do I, in order to create this hash function, remember this is h of u is from some set of hash functions, right? So this was a random choice. The randomness was in the choice of the hash function. What was random about it? What's the randomness defining this hash function?
Oh, the unit vector?
Right, so this u is the random choice. So the u, for h of u, the u needs to be a random unit vector, right, in RD, right? So, okay, so good. We talked about, and so let's say the only thing that I can do for randomness, though, the only thing we talked about is either A is going to be uniform random in 0, 1, or B is going to be a rand bit. So it's in 0 or 1. Right, so these are the only things I told you how we could do randomly. And so typically on built-in, these are the two options you have. Usually you just want to use this one. You want to generate a random value uniform between 0 and 1. There might be other things built in, but probably not a random unit vector in RD. How would I do this? How do I generate a random unit vector?
Random angle. Just a random angle.
Okay. Yeah, so a random angle. Okay, that works well in 2D. In 2D, you're right, that's a good insight. I can think of this as a circle, and then I have these radians which go from 0 to 2 pi, right? This is pi. I pick a random value between 0 and 1, I scale by 2 pi, and it gets me a random point on the circle. Maybe this value is like, this would be like 0.4 or something like that. After I scaled, maybe that would give me that point in the circle. That's my random unit vector in 2D. But in higher dimensions, it's not clear how to do this anymore.
Maybe we can just pick a random point, and then we have random value.
Okay, good. How do you pick a random point? What do you mean by a random point?
Like maybe we can just take a random sample, and then we correct the vector.
So you take a random sample and then you make it so it's a unit vector. Some random high dimensional point and then normalize it.
Yeah.
So what do you mean by random high dimensional point? So one common thing people would guess, and maybe this is what you're guessing, maybe not. You can feel free to wait to tell me whether this is what you wanted to say, whether when you find out whether it's right or not. So you have a random point in RD, and I'm going to say that each RI is going to be uniform 0, 1. Right? So basically, I'm going to get this box, right? So this is in 3D, where this is 0, this is 1, 0, 0. This point up here is 1, 1, 1. And I'm picking a random point in this box, and then I'm going to, there's some surface of things of length 1, and I'm going to normalize it to go here, so this length is 1. Right? So and this only gives things that have positive coordinates. It turns out you also want to allow things where, like, I may want a random vector that was going in this direction instead, and this had a y coordinate, or the x coordinate was let's say was negative. So instead of this box, I actually, I can do 8 of these boxes, or I can move the origin to the middle, expand it a little bit. Turns out this is not going to work well. The problem, let me draw it in I try to be fancy drawn 3D, but it's easier to illustrate in 2D. Okay, so this is, let's say this is 0, this is 1, 1, this is -1, -1. I can generate these random 0, 1 bits and scale them by factor 2, and then subtract 1, and I get essentially a random point in here, and then I want it to lie on this circle, so I map it down to here. So is this going to give me a uniform point on the circle? What's going to happen is you're going to tend to get more points towards the corners. And you're going to get fewer points on the axes. So for any point that winds up in the ball, those are all essentially equally likely, but you're also going to get these points up here in the corner. And these points in the corner always map down here. So these directions are going to get more points. And in higher dimensions, this will get even worse. Well, I think I have another lecture where we'll talk about some of these weird phenomena. In higher dimensions, and remember, this was for high dimensional data we wanted to do this with. In lower dimensional data, there'll be other techniques. But for high dimensional data, this is not going to work very well. You're not going to get uniform on the sphere. Okay, so instead, what you're going to do is going to be similar to this in that you're going to generate a point R in RD, and you're going to generate each coordinate independently, and then you're going to normalize those to get it so it's a unit vector. But we're not going to use the uniform distribution. What we're going to do instead is we're going to get a point G in RD where for each I, GI is going to come from a Gaussian random variable or a normal distribution. So a normal distribution has a really cool property that a high-dimensional normal, if you restrict it to any one-dimensional space, looks just like a one-dimensional normal distribution, right? So normal distribution is a Gaussian distribution, looks like this, right? So the height here, if I didn't normalize it with a value x from 0, is going to be, this value is e to the minus x squared. Roughly is the property. Now there's, you divide by the bandwidth and some other normalization stuff, right? But it's decaying away from 0. And so if you draw this in higher dimensions, you're going to get, say, more points here, and this is decaying as it gets further away from the origin. And to generate Gaussian high dimensional Gaussian random variables, all you need to do is to generate a bunch of one-dimensional Gaussian random variables. And the fact that I drew this as circles, that's important. It's symmetric in every dimension. Right? If I rotated the bases, they still look the same. Because it's circular, the level sets of this. So the value, the value of the PDF at any distance from the origin only depends on the distance from the origin. It only depends on this value, this distance x. That only governs the height here. So what I do is I generate these high-dimensional Gaussian random variables, and then I normalize those, and that is uniform on the high-dimensional sphere. This is a really kind of cool trick, and it'll be important in a few ways, including in this context. But how do I generate these Gaussian random variables? So it turns out there's a trick called the Box-Mueller transform, which basically takes two uniform random variables, let's say U1 and U2, and it's going to create two Gaussian random variables, G1 and G2. It's minus 2 natural log of U1, square root of this, times cosine 2 pi U2. It's U1. Yeah, so don't ask me, I won't explain why this works, but turns out, so if you generate two uniform random variables, you can get two Gaussian random variables this way. And so this allows you to generate these Gaussian random variables, and then you can normalize them and get to get a random unit vector. And this random unit vector will allow us to build this this hash function for the Euclidean distance.
I have a question about the hash function. Why
Yeah.
we have to take mod? Why we don't just use the dot product?
The mod. So the mod is where is this? Okay, yeah. So right here. So right here, we took the dot product and we did the mod, and then we rounded to an integer. Okay, so what we wanted to do is we wanted to give, we wanted to give kind of snap this to an integer value. So the dot product is going to give us a continuous value. It's going to be kind of it's still going to be a fractional value. So I want to round it to the integer, so anything in here gets a value 0, anything in this bin gets a value 1, anything in that bin gets a value 2. And if I don't take a mod, I'm going to get to an infinite number of these things. I don't really need a mod. I could just have an infinite number of bins. And maybe you can do that, but it's easier for a storage space to say, I have a finite number of bins I'm going to do, and I might get some other spurious collisions, but I won't get too many. There's some flexibility in what the probabilistic arguments need to be, so I can deal with that. So this could be a finite number of these different bins I can do.
I'm sorry, on the Box-Mueller transform down where you
Yeah.
define G2, was that the square root of 2 natural log of U2 or U1?
Yeah, I think this is, let me write these. This is U2 and this is U1.
Okay.
The only difference is the sign of those. Those basically make them so they're orthogonal to each other. These two, I think, are strictly not independent of each other. Turns out you can still use both of them, and it turns out it's going to be okay. Because together they essentially represent a random thing on a two-dimensional, in a two-dimensional space, and it works out okay. So you can still use D random uniform random variables, or if sometimes people will just use the first one. That's also fine. Okay, so let me quickly argue that this hash function I defined is going to satisfy this property. I want to say that the probability that I have a collision, let me draw a new picture here. Right? So I have 2 points, P and Q, and I'm going to pick a random vector U. Okay, so and I'm going to set some length of the bin based on how big I take my mod and how I round it to integers. And so I want to argue that, and I won't go through the constants, you can work them out in the notes, but that if they're similar, they're likely going to wind up in the same bin, and if they're not similar, they're unlikely to wind up in the same bin. Okay, so first of all, if the similarity I want, if the bin width is going to be is W, and so the distance between P and Q is less than W over 2, then they're going to wind up in the same bin with probably at least 1/2. Okay. All right. I think if the width is, if the distance is less than W, I think it's at least 1/2. Right. The only time, so if I do a projection, so the other thing, because a dot product is a linear operator, then this is equal to P minus Q as well. So I can basically take the vector. That means I can take this vector, which is this vector here, and project this vector down. And a dot product is a projection, so I know that this is less than P minus Q. So the dot product only shrinks the distance. So I know if they start less than a radius W, they're going to be projected to less than a distance W. And then if I randomly shift, I think the argument is over 2 here, okay? So then if they're less than a distance W over 2, and I randomly shift, the probability of hitting the boundary between the bins in the middle is less than 1/2, right? So if I look at a width, let me switch colors. If I look at a value of width here, starting at the first point, the projection of P, then it's uniform, because I've done this essentially doing a random shift here. I probably need to do a random shift in that in the hash function here. So this probably should have been this plus some random shift value here. So if I did a random shift, then the probability it falls in between here, if this distance is less than W over 2, is less than 1/2. So the probability that they are in the same bin is greater than 1/2. Okay, so if they're close, I'm likely to have them in the same bin. If they're far, I want to argue I'm unlikely. Right? So now, this is the close case, and then the far case. So let's say that P and Q are here, and so now the only way I can get them less than some, if the width is again W. The only way I can get them less than a W is if the unit vectors fall in like a cone here. So if the unit vector is right here, then they're going to project down close to each other. If the unit vector is this way, then they're going to project far apart. So if P minus Q is greater than 2 times W, then the angle, essentially, it turns out I can think of angles because the unit vector P and Q they always lie in a plane together. There's some plane that goes through the unit vector P and Q. So I can think of the angle between the line between P and Q and the unit vector, and the angles for which they project to something where their width is less than W. They can't be in the same bin if their projected distance is less than W, is going to be some narrow band of these angles. And this is going to be something like also less than, say, 1/3. So the probability my unit vector falls in here or in the opposite direction is going to be less than 1/3 if so we'll be less than 1/3 if they're further than 2W apart. This is roughly the argument. Okay, so hopefully, so it means you can use these hash functions as well for very high dimensional points in Euclidean space. And the thing is, the number of hash functions you use and the accuracy is independent of what the dimensions of the points are. So these can be arbitrarily high dimensions, and this is kind of a cool trick. If you've heard of the curse of dimensionality, which we'll talk about in next week a little bit more, then this is dealing with really high dimensional data can be really hard to do if you're using like 2-dimensional intuition. You have to use tricks like this in order to deal with really, really high dimensional data. Okay, so we're out of time. So it turns out you can do stuff for the L1 distance instead of the L2 distance, and there's some stuff on p-stable random variables in the notes if you want to look at it. Next week, Monday, we'll talk about other distances and some properties you'd want to have with them. Variations on these Euclidean distances as well as more exotic things. And then the following Wednesday, we'll talk about other techniques in kind of medium dimensions. This works if you're like in 100 dimensions, this might be the right thing to do. But if you're in 3 or if you're in even 10 dimensions, there are other tricks you can do to solve both of these problems that often work just as well. Okay, and then we'll start using those distances in clustering and so forth after. All right, remember to turn your projects on Monday. Right?